So far, a total of 118 elements have been discovered, and among them there are quite a few that we almost never hear about in our daily lives. The element we're looking at today is one of those that makes you wonder if it actually exists, but interestingly, it's named after a place everyone is familiar with. It's called Californium, an element named after the state of California. And just like its unique name, this element also has very distinctive physical and chemical properties. So what's the story behind Californium, the element born in California? Today, here in the Dr. SciVera studio, we're going to dive into exactly that. Before we begin, make sure to hit that subscribe button down below. Now let's get started. Following World War II, the world had witnessed the power of the 2 atomic bombs dropped by the United States on Japan, and nuclear science was rapidly emerging as a matter of national interest. In particular, the idea of manipulating the atomic nucleus to create new elements was such an innovative field that it led people to rethink the very concept of elements for the first time since Mendeleev created the periodic table. At that time, the radiation laboratory at UC Berkeley, a world-renowned university located in Berkeley, California, had experienced synthesizing transuranium elements heavier than uranium, such as plutonium, element 94, and americium, element 95, and was pushing the boundaries to create yet another synthetic element. In 1950, as a result of that challenge, they succeeded in synthesizing californium, element 98. The Berkeley research team conducted an experiment in which helium nuclei, also known as alpha particles, were accelerated to high speeds and collided with curium, element 96. It is a process similar to firing a very small projectile at high speed to strike a target. When the fast-moving helium nucleus collides with the nucleus of curium, the impact causes neutrons to be ejected from the curium nucleus. Then the 2 protons from the helium nucleus fuse into the nucleus. As a result, with 2 protons added to the curium nucleus, a new element with atomic number 98 is created. So far, what do you think? Does creating a new element sound not so difficult? Although this process sounds simple, in reality it is an extremely difficult experiment requiring precise control over numerous factors such as the speed and angle of collision, as well as the size and purity of the target material for the reaction to occur at all. Considering that the synthesis of new elements is still not easy even today, it is easy to see how much attention this achievement must have received in the scientific community at the time. Naturally, the research team must have also felt a great sense of pride, and that sense of pride is reflected in the name of the element. The new element with atomic number 98 was discovered in California, and the Berkeley team wanted to express their respect and appreciation for the region and the university that supported their work. So they named the element Californium, after California. Scientists name elements for various reasons, but when an element is directly tied to a specific place like this, it carries a strong narrative on its own. It gives Californium the sense of being an element that represents California. Now let's take a closer look at what kind of element Californium actually is. First of all, Californium doesn't exist naturally on Earth. It is an element that can only be produced artificially. Although Californium is classified as a metal, it is a far cry from the metals we usually think of. To begin with, it is highly radioactive and extremely dangerous. Also, since it can only be synthesized in extremely small amounts, it is very difficult to pin down its exact physical and chemical properties, such as its melting point and structure. Its color is believed to be a silvery white like typical metals, but even that is not entirely certain. Californium also exists in several different isotopes, meaning it has atoms with different numbers of neutrons. Among them, Californium-252, made up of 98 protons and 157 neutrons, is the most well-known. This isotope undergoes spontaneous fission, continuously emitting a large number of neutrons, and it is exactly this property that makes Californium-252 so special. The neutrons emitted from Californium play an important role in various fields. To understand how, let's use a simple analogy. Now let's try a simple thought experiment. Imagine there's a metal cup, a plastic cup, and a glass cup in front of you. This time, you're blindfolded and you have to figure out which is which. The problem is you can't touch them directly. Instead, you're only allowed to use a small metal rod to examine them. So, in this situation, how would you tell the cups apart? What if you tap each cup one by one with that rod? What would you hear? The metal cup gives off a sharp metallic ring, the plastic cup makes a dull thud, and the glass cup produces a clear, high-pitched chime. Because different materials vibrate differently depending on their structure, we can distinguish them just by the sound. The same principle applies to atoms. If you want to know what kind of atoms are inside a material, you have to tap them. But atoms are nothing like the metal, plastic, and glass cups we just imagined. They're far too small to be tapped with a rod and examined directly. So we need another way to probe them. That's where neutrons come in, acting as that rod for us. When we beam neutrons at the material we want to analyze, those neutrons collide with the atomic nuclei inside and cause the atoms to vibrate. In this process, each atom gives off its own unique signature. By analyzing these signatures, just like identifying the cups placed in front of us, we can identify exactly what elements are present inside that material. And the substance that provides a steady stream of neutrons to play that rod-like role is californium. One real-world application of Californium-252 is in oil exploration. To find oil, we need to understand what's hidden deep underground. But since we can't see through the ground, it is very difficult to know what is there until we actually start drilling. At the same time, we can't just drill holes randomly everywhere. So instead, oil companies drill a deep well and lower sensors down into it to scan the geological layers. In general, they analyze signals such as natural acoustic waves or various types of radiation, like gamma rays, to map out the subsurface structure. However, these methods have limitations. They struggle to accurately tell the difference between water and oil, and to precisely identify the composition of the geological layers. To overcome these limitations, a new approach was introduced, one that uses neutron scanning. In this method, neutrons are emitted directly from the exploration equipment, effectively tapping the subsurface layers and analyzing how they respond. For example, a formation rich in water absorbs neutrons very effectively, while an oil-rich formation shows a clearly different response. By interpreting these signal variations, the equipment can determine much more precisely whether a layer contains water or whether it is likely to contain oil. In the end, the accuracy and clarity of neutron-based subsurface scanning depend heavily on how many neutrons can be delivered in a stable and continuous way. That is why the performance of the neutron source becomes so important. In actual field operations, a material called americium beryllium is commonly used. It emits approximately 7.5 million neutrons per second per gram. For many standard exploration tasks, this level of output is often sufficient. However, Californium-252 operates on a completely different level. Californium-252 emits about 2.3 trillion neutrons per second per gram, and it does so very stably and continuously. In other words, it provides more than 300,000 times the neutron output of americium beryllium. As a result, the signals returning from the subsurface become much clearer, allowing for more reliable analysis. But despite this level of performance, Californium-252 has only been used in very limited and specialized situations. Why is that? Californium can only be produced in a very small number of specialized nuclear reactors around the world, and even then, the total amount produced each year is only a few grams. In fact, the only countries with officially confirmed production capabilities are the United States and Russia. This alone shows the level of technology and investment required to produce californium. Although its exact market price has never been officially disclosed, it is estimated that even just a few milligrams can be worth millions of dollars. Because of this, californium occupies a very unique position. It is absolutely essential where it is needed, but it is not something that can be used just anywhere. For this reason, geological exploration using Californium-252 is not considered a general technique, but rather one that has only been used in limited specialized situations. So, what do you think? Doesn't the story of californium somehow remind you of California itself? So then, why would we go to such lengths to create something so unusual, so dangerous, so expensive, and so difficult to produce? In general, elements that exist naturally tend to be lighter than uranium. Heavier elements, known as transuranium elements, do not typically occur in nature. However, by synthesizing these heavier elements and analyzing their properties, scientists have been able to uncover the fundamental principles of nuclear science, such as how nuclear reactions occur, how neutron capture takes place, and what kinds of electronic structures these transuranium elements have. Californium is no exception. It is not simply another element added to the periodic table. Rather, it shows how far we have come in understanding the atomic nucleus and how precisely we are able to manipulate it. Today we explored californium, an element with a story as unique as its name. What I find most interesting is not just its scientific and industrial value, but the fact that it exists only because of human effort. By pushing past the limits of the periodic table set by nature, humanity continues to expand those boundaries through collective knowledge built on science. And to me, that is something that remains remarkable, no matter how many times I think about it. It is worth imagining just how far this expansion can go. With that, we wrap up today's story. I will be back next time with another topic. I'm Dr. SciVera.